Right, today we're going to take a look at Euler's formula. Some say one of the most beautiful formulas that exist in mathematics. Before we get to Euler's formula, though, I'm going to introduce something called Maclaurin series. So what it does is it gets a function but turns it into an infinite sum. There's the series for e to the power of x. So it's the sum of x to the power of n over n factorial going from 0 up to infinity. It's an infinite series. What this allows us to do is to turn a function into a polynomial. So this e to the power of x becomes a polynomial function. So there's the two graphs there. The black one is e to the power of x. The blue one, obviously I couldn't put in an infinite number of terms, but the blue one I just went up to the first three terms there. So 1 plus x squared plus x cubed on 3 factorial. And you can see around 0, it's very good. It's very good. The more terms you have, then that blue curve starts wrapping onto e to the power of x. So when you get an infinite number of terms, it would sit on it perfectly. Cosine function. There's the cosine function. So negative 1 to the power of n over 2n factorial times x to the power of 2n. So there's the two curves compared. Again, only taking the first few terms of the infinite sum. The black one is cos x. The blue one, I've gone up to x to the power of 6 on 6 factorial. Again, around 0, very, very good. More terms you've put on, it would start wrapping around the cosine curve. So that turns the cosine function into a polynomial. The sine function, something quite similar, but you'll notice now it's the odd factorials on the bottom and the odd powers. So there's the two comparisons there. The black one being y equals sine x, and the blue one, well, I went up to x to the power of 7 on 7 factorial there. Once again, around the origin, very, very good. More terms we have, the better it'll be. All right, so why show you all this? This is how we get Euler's formula then. So we got imaginary numbers, but that now allows us to convert between exponential and trig functions. So if we let x equal theta in that Maclaurin series expressions for both cosine and sine. So cos theta will be 1 minus theta squared on 2 factorial plus theta to the power of 4 on 4 factorial and so on and so on. Sine theta would be theta minus theta cubed on 3 factorial plus theta 5 on 5 factorial, so on and so on. Now, x equals I theta in the expression for ex. So the Maclaurin series for e to the x, if I'm going to replace I theta now, we'll get 1 plus iota theta plus iota theta squared on 2 factorial plus iota theta cubed on 3 factorial and so on and so on. Now, because we've all expressed these three things now as polynomials, infinite sums, I can start joining the two together because I squared is negative 1. I to the power of 4 is positive 1. I to the power of 6 would be negative 1 and so on. And then the I cubed becomes negative I. If I break that into real and imaginary, look what happens. Okay. So the real part is the Maclaurin series for cosine theta. The imaginary part is the Maclaurin series for sine theta. And so there it is, cos theta plus I sine theta. So we can convert our complex number from a trig expression into an exponential. Now don't panic, you don't have to know the Maclaurin series. I just show it to you, say, look, we haven't just pulled this out of thin air. There is a relationship between the two. It's going via the polynomial, we get there. So all right, there's the formula. E to the iota theta is equal to cos theta plus I sine theta for all real theta. So we now have a third way of expressing complex numbers. Yes, we have using Cartesian coordinates, x plus iy, so that's Cartesian form. We then had mod arg, so r cos theta plus I sine theta, mod arg form, also known as polar form. But now we have exponential form. Now, Euler's formula was just e to the iota theta, but it's nothing to just multiply both sides by r to get the full complex number. So it becomes r e to the iota theta would be r cos theta plus r I sine theta. So now, 4 minus 4i, if I want to put that in exponential form, remember we already found the modulus in the argument of that. It was 4 root 2 for the modulus, minus pi on 4 for the argument. So if I was now to put that in exponential form, it'll become 4 root 2 e to the power of minus I pi on 4. So this allows us to do multiplication and division in a different way. So I can go root 3 plus I for z, 1 minus root 3i for w. Z times w. Well, if I change them into exponential form, the first one becomes 2e to the I pi on 6, 2e to the minus I pi on 3, but now I can just use index laws. Another reason why when we're multiplying we add the arguments, because we're actually using the index laws on the exponential form. And so we get 4e to the minus I pi on 6. We then could convert back and we get the 4 cis minus pi on 6 and then convert back again into Cartesian form, and there's our answer, 2 root 3 minus 2i. Z divided by w then, so the 2's will cancel. E to the I pi on 6 divided by e to the minus I pi on 3. Again, using our index laws, we subtract the powers, we get I pi on 2, well that's just I, because the argument's pi on 2, so we know that one's going to be just an imaginary, or z to the power of 5, well that'll be 2 to the power of 5, e to the 5i pi on 6. Again, we can then sub back in and get 16 minus 16 root 3i, and so on. So here, there we go. So Euler's, yet another way of playing with complex numbers.